So you may have heard our pre-conversation, lecture conversation here. I've known our speaker, I've not met her, but I've known her since 2005.
Mhm.
And probably shortly thereafter, I've been pestering her to give a lecture. And 15 years
15
later,
years later.
we are here. So in the interim, so her first faculty position was at Iowa State University. And then she was a visiting professor in the chemistry department at MIT. So just some highlights, you know. And then in 2016, she joined the Department of Chemistry and Material Science. Is that a joint department or joint appointment?
It's a joint appointment. So our material science is an umbrella division that
Okay.
everyone has a primary appointment in, like chemistry, physics,
I
mechanical engineering, and then we're also part of the material science program.
okay, okay. And she just within the last year or something got promoted. I don't know when that promotion was to associate dean of graduate school of the arts and sciences. So she's doing both research and administrative stuff. I basically her research that she'll talk today and her research focuses on development of organic semiconductors. And I think when you mention her name, that's probably the next two words that would come to mind. I think it's fair to say that she is one of the foremost experts in the world on organic semiconductors. And it's really, I must say too, she's a Brooklyn native from New York. Yes,
I am.
New Yorker in the
I
house.
am.
And so it's really a pleasure to have you here to present on your research. Thanks for accepting our long-standing invitation.
Thank you, Desmond. And I feel bad that it went on that long, but life is just funny like that. I mean, when you first asked me, I was just getting started and I was like, I don't have anything to talk about. And then when I actually got to the place where I got something to talk about, everybody was asking me to talk about it. And it's just interesting how that worked out. And then I moved, and then I kind of laid low for a little bit when I moved because I was like, I got to regroup. When I shifted my lab to Boston, and then you circle back, but it's perfect timing because how can you say no when you could do it from your, you don't even have to worry about connecting flights. So it's,
That's
you don't
right.
even have to. Which honestly was the barrier because you guys are a little bit kind of tucked away a little bit out there. It was a
Exactly.
weird, you would think it would have been more convenient from Iowa, but it actually was probably easier from Boston. You know,
Probably
he,
is. It probably is.
either either way, you're gonna have to connect to Detroit, right? So.
That's true. That is true.
All right. Well, anyway, thank you everybody for taking this time this afternoon to come to my seminar. The title I gave the presentation today was "Making Molecules," and I often use this title because it gives me just kind of a blank slate to talk about whatever comes to mind as the dates approach. And I like the term "making molecules" because at the heart of my research, that is what we do. And I'll tell you more about why we do it and why we make some of the molecules as we lend ourselves to applications. But it's always about for us making molecules. And so let's see, slide advance with Zoom. So I will tell you I'm going to tell you a little story today. I won't have a chance to talk about everything we do, but I kind of group our research projects into some key areas. We spend a significant amount of our time making materials for polymer solar cells. And these materials are these so-called conjugated polymers. And I'll give you a little bit more of a backstory about that. And they're composed of various different heterocycles, different combinations. We append these flexible alkyl side chains, which helps us solubilize the polymer, makes it easy to dissolve into liquid, and then we can process films from it and fabricate the devices. And so we've making a bunch of these different polymers, and we've had moderate success. This quantity PCE is photocurrent efficiency. It's a measure of the effectiveness of the device. And so we get something around 3% we've actually gotten a little bit higher since then, but then you have to like verify it. So you want to make it repeatedly. You don't want to just report your best number. But we've gotten some consistent threes and some things that are high that we're trying to optimize. We've also spent a significant amount of time making polymers for light emitting diodes. And these are some examples of systems that we've made in our lab. Here's some cool pictures. This is actually our little this was actually one of our first working OLEDs. We were so excited. Nothing's more exciting. I think as a synthetic chemist, you're excited when you get that NMR and your product's actually your product. That's step one. And for us, the second step is when your product is actually your product and then it does what you think it's going to do. And our device actually lit up. So we're really excited about that. And some of our objectives in making light emitting materials is we target blue light emitting materials. And that's because blue is actually the hardest color to achieve of the three primary colors. So red, blue, green is what you need to make a functioning display. And blue is the hardest to achieve. And so when I found out blue is the hardest, I thought, well, then we want to make blue. You know, we're not going to be ordinary. We'll be extraordinary. You know, my students said, "Can we make green?" I'm like, "Green is basic. We're going to make blue," and so we do. But sometimes you end up with green. Actually, the thing is, I told my students, "Why we try to make green? When you fail at making blue, you end up with green. So we don't want to try to make green." The new kid project on the block is a project called Synthesis of Heteroacenes. And again, the title of this talk is Making Molecules. And if anything exemplifies that we make molecules, it's this project. We are just making these big annulated structures. How many benzenes can we annulate and how big can we make this system? And then what happens if we do it? That's really the crux of this project. How big can we make it? And then what does it do if we get it? And so my student Amy's actually chugging away at this. And it really starts off with this fairly simple molecule. I'd be shocked at how easy it is to make something like this. But then we take it through multiple steps and iterations, and I color coded it. So here's the main ring systems, black and blue. And then we do a cyclization to form this ring system. And then we annulate and we add on this red ring and it forms in situ this purple ring. Lots of fun. Crazy chemistry. And so Amy's pushing her way through that. And then we're going to see what it can do. Our thoughts behind this is that they're actually going to be what we call transporting materials and that we can use them in transistors. So that's going to be the cool part about it. But what I'm going to spend my time talking with you all today, and I thought this would be a nice compact story I could tell, is the synthesis of molecular organic semiconductors. And this is a project that we've been working on for the last couple of years, actually. And the goal is simply this: how can we make tunable materials? And by tunable meaning, how can we change some of the fundamental properties of the material? The color of light that they emit, the color of light or the wavelength of light that they absorb. Those are some of the key parameters that we're interested in. How can we manipulate that? And it turns out with organic electronic materials that how you combine these different structures. So we start off with this basic core. This is a benzobisoxazole unit. I'll talk more about that. And we substitute it with different types of arrow groups. And we can manipulate the properties of the system just using this basic motif. And it's pretty straightforward, but if you even just do some back of the envelope calculations or permutations, and it's like, oh, if I have 2 different places to substitute and I have 15 different heterocycles, how many molecules can I make? Yeah, if anybody has that number, let me know. But basically, that's kind of the crux. The answer is it gets very large because I know we have this matrix where we're characterizing properties. And so I thought I'd tell you this story, and we've learned some cool things about it since that time. And all of this work we do in my labs right there in the Fenway Park area of Boston, Massachusetts. And it's funny for me because now I mostly remote work from my home these days, but my lab is still up and running. They're essential personnel, so they come to campus. And we have a great view. This is actually an aerial view from a stock photo from the campus, but we're down here, the infamous Citgo sign, if you ever watch Red Sox baseball. And some of these red brick buildings right over here, this is where chemistry and material science is. And on our upper floors, we actually can see into Fenway Park. So that's pretty cool. At least through this year, there's a rumor that they're actually going to put another big building like right across the street from us. And I think it's going to be like 20 floors, 25 stories. So that building's going to come up here and totally take out our Fenway Park view, but we'll enjoy it as long as we have it. So why do we care about these materials? Well, it really has to do with technology or the evolution of technology. And, for the younger people in the audience, you probably are laughing like that was a cellular phone, but this is kind of how things were. We keep trying to make our devices smaller, lighter, but at the same time more powerful. And it would shock you, to learn that the computational power we have in a cell phone exceeds what was available to us even for some of the top range computers, 20 years ago. And so the technology is moving forward at a fast pace, but all of this requires new materials. From the polymer side of the house, we need structural materials to just safeguard these things. Lots of research are going on into, crack proof and drop proof and shatter proof casings to keep everything safe. But on the inside, we need to look at materials for data storage. Energy storage is a huge thing, right? We have these super awesome devices and we're always, running around looking for outlets to charge them back up. And then also the displays, keeping it bright, having good color clarity and resolution. It's amazing where these things have evolved. But all of this has been impacted and enabled by lab research, the design of new molecules, new materials. And so I highlight these cell phones from the old heads. This is kind of how we started and we got into the slick iPhones. But for your newer people, the evolution looks more like this. But the heart of the issue is still the same. We're getting lighter, we're getting more powerful, and all of this is enabled by new materials. These numbers are going to be hard, actually easier to read because we're from home, but you can see actually these numbers below is actually the weight in grams. And so we can see now that, these things are less than 200 grams each in terms of the weight of the foam, much lighter than what they used to be. Ironically, one of the things that drives us on the research end is to also make better materials and to make them efficiently to keep the cost down. But as I see the price is shooting up for these devices, I don't think that Samsung and Apple are going to pass any of the savings on to you, the consumer, but it still motivates us in the lab. So how do we look at the evolution of materials? Well, just like, we need to make new devices, materials have evolved a lot over time. And if you go back to the very beginning, man was restricted to access to natural materials, things like cotton, wool, and silk. This is what we had available to us from natural sources. And this is what we use for all of our fabrics and fibers. And so the evolution of materials was such that we started to make synthetic materials, things like nylon. Nylon was a big deal when it came out. It was one of the first synthetic polymers. And it showed us that we can actually make materials in a flask under a lab setting. And initially, people tried to make nylon as a synthetic replacement for silk because silk was so highly sought after. And nylon has some similarities to silk, but it is not silk. And people kind of stuck with that. Nylon is nice, but it's not as good as silk. And that's true. But maybe synthetic materials aren't meant to be identical to the natural ones that they're replacing. Maybe synthetic materials can actually have new and different properties that we can achieve from naturally occurring materials. And so a good example of that is Kevlar. We don't have any bulletproof naturally occurring materials, right? So that's a nice win for synthetic materials. Or something like polyethylene terephthalate, which is literally the most versatile plastic in the world. We could do all kinds of stuff. It's the material that's for your plastic bottles, and at the same time, it can also be spun into fibers to make polar fleece and flannels. So lots of utility for synthetic materials, and now the number is just vast, and most of us can't even imagine our life before we had synthetic materials. But if we now look back to the periodic table to where nature begins, we see our semiconducting elements. These are things like silicon, germanium, gallium, indium, arsenic. These are our semiconducting elements. And in fact, they're kind of the cornerstone for a lot of our technologies today. People always think about the computer industry. We think about Silicon Valley, silicon microchips, and that is certainly one of the backbones of it. Also, silicon's used in solar cells panels. But we also have large numbers of these other semiconducting elements that are doped into it. But this is our main playbook. So now as chemists, we ask ourselves the question, well, can we synthesize semiconductors? And the answer is yes. And most importantly, we can do this using organic materials. And as we know, organic, the old school people would say organic meant it came from living species, but now we know it to be carbon-based materials. And in fact, Earth is a carbon-based society. There's no more abundant element than carbon. So why not make carbon-based materials? And so it turns out that we can actually synthesize organic semiconductors. And we can do this in a number of ways. We can make conjugated polymers. I'll tell you a little bit about that. We can make these infinite small molecules. Single crystals are kind of a subset of small molecules. Some small molecules have the ability to form very large crystals, and there's some unique things you can do with them if you can make a large crystal. And these fullerenes, or these C60, C71 spherical Buckminster fullerene type systems as well are part of our playbook. So what exactly is an organic electronic material? By definition, these are small molecules or polymers that exhibit semiconductive properties. And these materials derive these properties from the delocalization of electrons within the extended pi conjugated backbone. And so this is a simple band diagram, and this is looking at something like ethylene. It's conjugated. We have a double bond. We have sp2 hybridized carbons. It's the simplest alkene out there. It's a very wide band gap material. We would call it an insulator. It's got extremely large band gap, 6.7 eV. It absorbs in the UV range of the light. nothing too spectacular. But what we see is if we extend conjugation, so now we have the butadiene example here, we've extended conjugation, we can now delocalize electrons. For those of you who've already done organic chemistry class, if you actually even try to do an addition reaction, you know how that carbocation likes to migrate. It's the same type of concept. Easily delocalize electrons, at least across this finite range. And as a result, we get a narrowing of the band gap to 5.8 eV. And as we increase the number of double bond units, we increase the number of levels. So we have our pi level, which is usually correlated to our valence level, our valence band, and our conduction band. We have our pi star. Or we can correlate them to our HOMO, highest occupied molecular orbitals, and lowest unoccupied molecular orbital. So what happens? As you extend conjugation out, these levels fill in, this gap narrows down, and in principle, as you get to the infinite case, which was what many scientists had hoped at some point, if you go to infinity, that these levels become less discrete and they behave more collectively. All these electrons delocalize as a band. And hopefully these two energy levels would be right on top of each other, no optical gap. We would just have a HOMO and a LUMO, and that would give us a conductor or a synthetic metal. Turns out that that's actually very difficult to do. There's this nice little thing called Perel's distortion. We never quite get our p orbitals to overlap efficiently enough to allow for a zero gap material, but we can get very narrow band gap materials. And so while many viewed that as a failure, because the goal is to, quote, make a synthetic metal, others said, okay, so it's not a metal, it's a semiconductor. Well, let's do semiconducting things instead of metal things. And in doing semiconductor things is where these materials thrive. And so I give you some examples here of how we can extend this conjugation. I mentioned that the gap narrows. This is just one example from the literature that shows it looking at the absorption spectra. So the UV vis, the lambda max in the UV vis spectra can be correlated to the band gap of a particular system. And as they increase the conjugation length for this material, they have 3 of these units linked together, and they go 2, 3, 4, all the way out to 11. And you can see this narrowing of the band gap as we shift out to longer wavelengths. So it's inversely related. Smaller band gap equals higher wavelengths of absorbance. So it shows us that it works, but more importantly, it shows us that while the theoreticians said, let's go to infinity, we don't need to go to infinity. We can go to a very small, we can actually go to a very finite number of units and actually get this convergence. There's not much difference here between the 11, and I think the blue one is the 6. So we don't really need to go very big to get there. And how we can get there, the number of structures is just so large. And you get there by just making different combinations of heterocycles. You can substitute them with heteroatoms. Like here's some oxygens. We can have alkyl chains, alkoxy chains. You can connect them with single bonds, double bonds, triple bonds. The only requirement for extensive delocalization is that you only have sp2 hybridized carbons. So if you have this alternating backbone of sp2 hybridized carbons, then you can get delocalization of your electron density. You introduce an sp3 carbon, it kind of becomes a trap or a dead spot. The electrons won't move through it. And for the most part, many of your heteroatoms can also participate in this delocalization. Sulfurs, oxygens, nitrogens, they all work pretty well. Seleniums, if you're feeling ambitious. And so this just shows how we characterize our systems. And again, different ways we can get here. Here are just some more examples. An N-type system is a system that likes to pick up an electron. So we can think about it, as anion or negative charge delocalization throughout the system. Whereas our electron-rich systems like to donate an electron, and then they'll have a vacancy. We call it a hole or a positive charge. A hole is kind of a variant of a carbocation, and that will be the species that will be delocalized throughout. But nowadays, we tend to make these so-called donor acceptor species where we put N-type or electron deficient units with P-type electron-rich units, and we alternate them in the backbone. And what's cool about that is you can actually play around with the relative strengths. If you have something that's really electron donating with something that's really electron accepting, you can get a very narrow band gap material. And if you have something that's weakly donating or weakly accepting, then you can widen the band gap out. And so we can make a whole range of materials. This is some examples from my lab. My student Dana, who actually graduated a couple of years ago now, made this beautiful set of materials. And she kept one unit the same and changed the donor strength of the other building block and was able to get a wide variety of materials made with different absorption properties. And she put them together in the rainbow for fun. We always have fun in my lab. So we try to have fun. So what are we interested in this? I mentioned about the impact on technologies. Organic electronic materials have done so much for the fields. We are making materials for transistors. That's kind of the inside, the circuitry of your devices. And we can really have record high mobilities. Back in the day, this was a dream. Like, oh, you'll never make an organic material that even pass current. And it's like, we'll make an organic material that passes current on the same order of magnitude as silicon. And it's like, oh, shocking. And people would say, oh, you'll never make an organic material that can effectively harvest solar solar light and turn it into energy as well as silicon does. And again, where silicon's still better, but we're at least in the same order of magnitude. And that's significant. When you're talking about 1 point something to, you're talking about 2 versus 20, that's a problem. But when you're talking about, 17, which is one of the record high PCEs versus, 25, we're still in the same ballpark. So, and organic light emitting diodes, just lots of new opportunities. They've kind of had a renaissance of late. They were kind of the early kids on the block in the 90s, lots of interest in organic light emitting diodes, and it died down a little bit. But now as the world's become more energy conscious, it's picked up. And, I learned a lot as a scientist about how policy and politics influences science. There really wasn't a reason in the world why OLEDs didn't start to replace incandescent bulbs years ago, other than the incandescent people, have a good lobby and kind of like, don't pay attention to those OLEDs. They're no good. They're no good. And now everybody's like, no, but seriously, they use less energy. We should pay attention. And so we're starting to see a renewed interest in it. So what do? I make materials based on a heterocyclic system known as the benzobisazole. And these are some examples here. And it's a really cool ring system. It's got a central benzene ring, and it's flanked with 2 5-member heterocyclic rings. And we can have in this heterocyclic ring, the common theme is there's always this imine nitrogen, this carbon double bond N, but then we have a heteroatom. It can be oxygen or it could be sulfur. And you can see the arrangement can be cis on the same side of the ring or trans on the opposite side of the ring. And we've done a lot with this. That's what I'm going to tell you about. We weren't the first. This guy Wolf did a tremendous amount of research on these materials back in the day. And what we learned from Wolf's research and even some early work by Sam Janicki is that these materials are awesome. They are N-type systems, so they like to transport electrons. Turns out most organic systems are P-type, so an N-type system is rare. And I mentioned I like difficult, so I said, ooh, N-type, we're going to do that. They have good photoluminescence, an entity known as nonlinear optical susceptibility, which plays into, again, the charge transport game, but these are actually very high and also very good for OLEDs. OLEDs said, yes, let's make it. The hallmark of these systems was their really bad solubility, which makes it difficult to process them, and the reaction conditions to make them were harsh. High temperatures, like 225-degree reactions using acid, polyphosphoric acid as your solvent. And I can tell you from experience, because I did that in grad school, not fun. I lost 2 very, very nice pairs of jeans due to with working up my reaction. If you spill polyphosphoric acid on your jeans are trash, just so you know. And also, pro tip, keep a spare pair of sweatpants in your drawer if you're working with polyphosphoric acid, in case you have to throw your jeans away. But one of the things that I challenged myself with is how to redo the synthesis and get away from this acid. And so we turned our attention a little bit to polymers in the beginning and also small molecules. And this just some more background. These are some examples from other research groups which showed that these small molecules are actually really cool. This was the first example of these cruciforms that kind of inspired me to do my project. Colin Knuckles' lab out of Columbia started to do these. They call these cruciform systems, and they got some really nice self-assembly and show charge transport in the system. And Colin's synthesis was absolutely awful. He used this reaction known as a Staudinger reaction, and it involved making a diazide. And if any of you keep up with the safety literature, azides aren't necessarily things you want to work with, and diazides aren't necessarily things you want to handle either. So we wanted to get away from it. Another group also showed great optical properties in OLEDs using these benzobisoxazole systems. So what I did back in 2005 when I first met Desmond and I started my research group is the first thing I did was to solve the acid problem, and we redid the synthesis. And this slide seems very straightforward, but it's a very subtle thing. The typical reaction mechanism to making these polymers is to start off with a diacid, so Z would be carboxylic acid groups, and you use the diamino diols or dithiols, and you do a condensation reaction, high temperature in that acid I've described, and you make the polymer. What we decided to do was actually do a 2-step process to instead make these heterocycles first and have reactive end groups on them, and then to just use a number of different carbon-carbon bond forming reactions to make polymers. So we just have to orthogonally pair Y and Z to something that will react with each other in the fashion that it will make a new carbon-carbon bond. And there's a lot of things in the literature that will do that. You can imagine that we could do Horta-Wadsworth-Emmons couplings between aldehydes and esters. We could do, if we have a halide there or alkyne, you do sonic sugar cross couplings. We did it all. And how we got there was really interesting. We made these reactive groups called orthoesters, and orthoesters are members of the acyl family. They really should probably belong in, probably chapter 22 of Wade or something there in the back with the acyl chlorides and the esters, but they don't tend to show up in undergraduate chemistry, but they are acyl derivatives. And, they have the same type of reactivity as you would expect an acyl derivative. They'll do great condensation chemistry, but they'll do it under lower temperatures than if you use a carboxylic acid. And unlike an acid chloride, they kick off alcohol as their side product versus HCl. And so it's a little bit more of a greener thing. And it actually turns out kicking off HCl is somewhat what leads to degradation and instability. So this was a nice, clean, and really good synthesis. We were able to make a lot of these, made a bunch of different co-monomers, made a lot of polymers. And so here are some examples from my lab. Here's the main heterocycle here. We flanked it with 2 thiophene. We cross-coupled it with this building block, which is a benzoyl dithiophene, and we made polymers for solar energy conversion. And these are those photocurrent efficiency values. We got 2.8 and 3.5 at the time, and this just shows the current density curves. When you make solar devices, you actually want a nice curve. You want it to be deep and square. And this could be a little bit deeper and a little bit squarer, but it shows us we're in the right neighborhood. Actually, we did this a couple of years ago, and most recently, right around the time of the pandemic, we actually remade a related system to this and got something closer to 9%. So for my students who were in the lab, it was really a testament to persistence, not to give up. The first student got us halfway there, just making it and showing it had a photovoltaic performance, and then the next student optimized it and basically tripled it. So we were really excited to see that coming soon. The other side of the coin, as I mentioned, the OLEDs kind of had a renaissance, and these little pretty pictures show why the world became more interested in OLEDs in the more recent years than they were 20 years ago. OLEDs have a lower energy consumption and also fabrication cost than conventional LEDs. And as such, you can make large area or flexible devices. And so you can imagine there's a lot of OLED interest in televisions. As you know, I remember when I was a kid, it was like, oh, we got a 19-inch TV, right? That's just like, oh, we got a 19-inch. Now you will get you will get laughed out of your friend circle. Invite somebody to your house to watch the Super Bowl on a 19-inch TV, and they will like unfriend you. But that was a big deal back when I was growing up. Now, it's like 50 inches, 55 inches, and all of that is being enabled by new techniques and easily processed LEDs. OLED's also really cool because you can combine, if you have blue OLED and orange OLED, you can make what we call a WOLED, or a white light organic emitting diode. And this is what's of interest for low energy consumption and light emission. And then the other thing that's cool for the devices, if you ever in Best Buy play around with the TVs, is that the on-off ratios for OLEDs are different than for conventional inorganic LEDs. So your black is, quote, blacker, and so your contrast ratio is higher. And so whenever a store like a Best Buy is showing you an OLED TV, they're almost gonna have something dark on, like this planet or like Batman, the Dark Knight or something, because they want to show you how nice the dark contrast is, which is harder to achieve in the conventional or OLEDs. But as I mentioned, blue is very difficult to get for a purely organic. You get lots of red and green emitters, but blue still remains the holy grail. So blue is where we jumped in. It turns out from the historical research on bisoxazoles, I knew that bisoxazoles tend to be luminescent and blue. And so we started to craft polymers around them. And early in, we had some great success. Some of our early polymers that we made, this is a chromaticity diagram, and it shows us that our blue is nice and deep in the far corner. As you look at the blue space, one of ours is kind of this tealish one. I think that was in the teal and the green one were in the picture in the beginning. As you get on this fringe, you start to lose your blue. You get more teal, more green. And on this fringe, you get more violet. So the deeper you are in the corner, the more pure or true blue or deep blue your system is. So some of our systems were really nicely blue. What came from this research is my student Jeremy, who was in the lab at the time, he looked at it and he says, Malika, we made a bunch of polymers and they all had condensation axes through this heterocyclic system in this fashion, connected through the 5-membered ring. And he said, but Malika, we can make a purely conjugated system if we went through the benzene ring in this direction. And I said, we could. He said, well, I wonder what would that do? And I said, I don't know. We kind of talked a little bit and hypothesized, but we were experimentalists. I told him to go in the lab and make it. We'll find out what it does. We'll make it. And so Jeremy made this series of materials. And what we found out is what it did. And this set was cool, but it was interesting because the connectivity was different. We had triple bonds versus double bonds. So it wasn't a true comparison. He then went back and made this system with single bonds where everything's identical except for the orientation of this heterocycle. And what we found, and here is, this is the luminescence efficiency, this value LE, 0.6. Here it is 2.2. So we can see that this is more than 3 times bigger just by changing the conjugation axis. So that we said, the direction of the connection actually impacts the behavior of the molecule. And so that was a very interesting result. And it really, in that time, you can see there's a gap actually between when we did the polymer papers, but in that time, we actually also started to do a whole lot of small molecules because I said, well, it would actually really be nice if we can just get down to exactly what's happening at a molecular level without worrying about some of the additional complications of polymers. And so we made these polymers. We made the small molecules rather, and we looked at two things. What happens if we substituted either along this 2,6 axis, which is through the heterocycles, or the 4,8 axis through the benzene ring? And so it turns out that we found that doing a lot of theory, because it's faster to calculate and predict the properties of these systems than it is to make them. And so doing a ton of theory, we found out that we could actually make both wide bandgap materials suitable for OLEDs and also narrow bandgap materials suitable for OSCs, which are organic solar cells. And so we set about to do this. We had a great theory collaborator, calculated dozens of structures for us, which was great. We threw out some of them as being useless, and then we honed in on a few that seemed to have the ideal properties. One such example was a series based on benzene and fluorine, and this heterocyclic system, or it actually doesn't have any heteroatoms, but this aromatic ring system is known as fluorine. In common circles. Here's our benzene, and we made this series of materials. My student Ramiro actually did this work, and it's really elegant because we do a two-step process. We start off with this starting material, we do a condensation reaction to introduce the aryl groups at the 2 and 6 position, and then we do a cross-coupling reaction to introduce them at the 4-8 position and repeat the process. You could take this batch and split it and make 2 different molecules that way, take this batch and split it, make 2 different molecules that way, and we quickly got at 4 molecules that look like this. And our goal was to make blue light emitting materials. Here's the photoluminescent spectra here. And we can see that all of them have lambda maxes that are centered around 450 nanometers, which is great. That's kind of the sweet spot for blue. But you can get there a number of different ways. So here's our emissions wavelength. So we go between 433 and 450 for our blue emission. And we got there with various combinations of the HOMO, LUMO, and then the band gap. And so, for example, we could look at numbers 2 and 3, small molecules 2 and 3. They have the same band gap, but their positions are very different. The LUMO for 2 is 3.4 and 5.7, and this one's downshifted 3.7, 6.0. That proves to be a relevant entity when we went into the device fabrication, because you don't just want to have a blue, you need a blue, that's step one, but you also have to think about where your energetics lie. And so if I show you this cartoon here, this shows our basic layout for our devices. This is how we make our OLEDs. And we make what's called a host gas OLED, that our material, the cool little material we made, we call it the dopant, and we mix it in with another material, which we call the host. More about that. And the reason you do that is we found that when our material is near itself, it likes to pi stack. The benzenes like to stack right on top of each other. And instead of emitting light, it underwent what we call non-radiative processes. If we could probably mentor it, I mean, it's going to be heat, but it's such a small amount, because you're talking about, microjoules and millimoles of material, but it became heat and not light, and that's not useful. But if you dilute your system, when we start looking at the solutions, they were brightly emissive. And so that told us that we basically needed to make a dilute solid. So we dilute our material into another solid, and then we can isolate these dopants and we can get the emission to go. And the key criteria for the host is it has to be something that can actually do energy transfer, this FRET, or this forced to resonance energy transfer. So we actually excite the system, we get energy transfer from host to the guest, and then the guest fluoresces, and it's a beautiful thing. This little device architecture, lots of little terms: aluminum, lithium fluoride, organic material known as BFEN. But here's where the magic occurs. These dots are the same as these dots, and I think, yes, this is the structure of CBP. But if we go here, there we go. I lied, Desmond. I said there wasn't a video. There is a video. I forgot about this one.
Okay.
Fun little video. It's going to play, though, because it's on my computer.
All
and
right.
so this is what happens. We excite our device. So this is the layout of the device. And we're going to pump in current. We're going to pump in positive charge carriers and negative charge carriers. And they excite the material. They recombine in our emissive material. And if you do it right, your material is going to emit light. And the color of the light is going to be dependent on the wavelength of the material. I mentioned the different energetics of our system, and this little band shows what happens. So all of them have different band gaps, but this is their HOMO, this is their LUMO and their HOMO. And what we can see here, the yellow is the band gap of the host material, is that the first one was outside, it was too wide, so we weren't able to make the device, but the others lined up neatly within it. And so we were able to explore them and see what their devices would look like. This is another band diagram of what's happening in here. Positive charge carriers coming from the anode, negative charge carriers coming from the cathode, and into our device to emit light. And this is just the structure of that molecule CBP. So what happened? The answer is what happened is it worked beautifully. We're very excited. This is the data for small molecule 4, and it is gorgeous. Nice blue. This little inset shows the color of the light that's emitted. 450 nanometers wavelength was the emissions maximum. We doped in different levels. And so we start to see a little bit of emission coming from that CBP host material at low percentages. But as we increase the concentration of our guest, we could suppress that down and then get neat light from our guests. And the key thing that we got, and there's a lot of numbers on this slide, don't worry, the main points are here, is that the brightness, this is the measure, one thing that we care about. We care about what color the light is, how bright is it, and how efficient is it? Like how much energy you're pumping in to get light out of it. If your device is not efficient, then you have to put a lot of voltage in, and these numbers get really big to get a good number of light out. But then often if these numbers get too big, you literally fry your molecules. So you want to have low drive voltages and get good efficiencies. So these are actually pretty good, comparable to what we got for our polymers from a small molecule. So we're really excited about that. So brightness was around 1500. The efficiency and EQE were around 1.9 and 2.2 respectively. The color was 450. And I showed you that diagram. These are the coordinates that help us plot that to the diagram. And the industry standard is actually that your first two values don't total 30. And so we're under 30, with the second one is the Y coordinate being less than the smaller of the two. So like as far as the industry is concerned, this is like the space you wanted to be in. So we were super excited. So in terms of optimization, we just needed to make it brighter. If we could actually get this number higher, closer to 4, that would be better. 5 is kind of like the upper limit for these things. So we were excited. Then we looked at the next system and we said, yes, and I can tell you structurally, all that we did here is this has the fluorine groups in all 4 positions. This one has the fluorines on this axis and the benzenes on the other 2 axes. And we did that. We got the wavelength shifted back 10 nanometers, still nice deep blue emission, very sharp. And the best performing device here, also at 2%, showed us, even with the similar drive voltages, that we had a brightness of 2152, so even brighter than the other one. And that we also had the efficiency in the EQE. And sorry, there's one more value in here that was missing from the other table, but we'll compare the two that were present. The efficiency and the EQE are similar to the previous one, and it was brighter, and it was deeper blue, because this Y value went from 0.909 to 0.5. So all that was exciting. And Ramiro, who did this work, was like, yes, I'm killing it. I'm like, Ramiro, you're killing it. And then this happened. We looked at the third one, and it really taught us a lot about the role of structure, because now the relationship between this one and the previous one is they're isomers. We have fluorine groups and benzene groups on this one. And when we go to the other one, we have fluorine and benzene, but we just changed their location. And in doing so, it was detrimental. Everything went wrong. One, we can see that while it has blue emission, there's this very strong shoulder that we never saw before. So instead of getting a single sharp color, we kind of had this shoulder, this dual emission, and it isn't very bright. The best one we got was less than half of what we got from the previous system, and also with significant decreases in all the key categories that matter. The color was good, but it was even still going more toward the UV. This creeped up. This number got a little bit bigger than the previous one. So the takeaway from this is we said, wow, it doesn't matter just what units we use, but how do we position them? And then we started to really dig into that a little bit, like what's happening here? What is the role of position in all this? And so, Desmond, am I right? Do I have about 5 more minutes?
Yeah, you have 5:11. So we have 5 more minutes, and then we could do Q&A.
All right, so I'll take you through this. So David, who's, and you can see like my group is kind of like a relay race. We keep passing the baton over the years, somebody gets started. I mentioned Jeremy in the beginning. Jeremy got us started. Jeremy graduated, got a great job. He handed the baton off to Brian. Brian took it and ran with it. And he graduated, got a great job. He handed it to Ramiro. And then Ramiro got a great job and he left David holding the bag. And now David is about to leave me and get a good job. So the moral of the story is I work my students really hard, but they get good jobs. So that's the plus side. So now David's with us, and David David said, you know what, Malika, I think we should do a parent-children study, is how he termed it. And I said, a parent-children study? And he said, yeah. And then we started discussing what he meant. And I said, oh, you're talking about heredity. And he said, yeah, I suppose so. And so, for those of you who took biology, you've heard of the term heredity, and it comes from the Latin word hereditum, but it's the condition of being an heir. And we know it to refer to the characteristics that you inherit from your parents. And so we just like, this is actually cool. Let's start thinking about molecular heredity. And we did some sci-fi searches. Only one other paper actually came out on molecular heredity, and it was right along the lines of what we were thinking. And so I present to you all the Brady Bunch. And for the younger crowd, you may or may not remember the lovely story of the Bradys, but they're basically a blended family. Carol had 3 girls who inherited her nice blonde hair. And Mike had 3 boys who had dark haired, good looks, just like their father. And as heredity would suggest, this is exactly what we would expect to happen. Now, unfortunately, the Bradys were a blended family. Mike and Carol had the children, then they got married, and then they lived together, and all the hijinks ensued. But we never got to see what would actually be the dominant trait between Mike and Carol if they had a child. Would it get Mike's dark hair? For those of us who know genetics, we know it's very likely. Would they be an oddball out and get Carol's blonde hair, or would it be a redhead? What would actually happen, and how do these genetic traits passed on? And so a better example is a more modern day family, John and Kate. Not only because they're more modern, they're also very different, dark hair, blonde hair, but they gave us 8 kids, and we could actually see the range of possibilities. In fact, many of these kids have John's dark hairs, but you do still get a few who have the lighter sandy hair, even though that's the minor trait. And then, further differences if we look at eyes and eye color and so on and so forth. So it tells us that progeny do inherit their traits from a parents, and often in a predictive fashion. What does this have to do with molecules? Well, let's look at our molecule and think about it as the sum of its 2 parts. And so I mentioned there was one example in the literature of molecular heredity, and the authors proposed just that this offspring, this child, was the summation of 2 parts. It had this one parent, which was SC2, they called this molecule, which had these phenyl rings and this carbazole, and it had this other parent, which was characterized by having, I'm blanking on this ring system's name, another phenyl group in a different heterocyclic ring. So they sandwiched these 2 pieces together and said, okay, which of these traits are inherited from each of these parents, and did some studies and did some predictive things. We felt like our system was even more susceptible to that because here's our cross-conjugated molecule, and we now refer to it as our child. And we can think about our child as the sum of 2 parts. Its linear parent, or the 2,6 parent, which comes through the heterocycles, and its 4,8 parent, or its vertical parent, which comes through the benzoxazole rings. And so we asked ourselves, if we were to actually make these linear molecules and characterize them instead, could we then predict what the properties of a cross-conjugated child would be? And it turns out, yes, you can. And so this is our lineup of characters that David decided to make. And so he made a bunch of these parents, and we thought for simplicity, we would make phenyl rings and these M-terphenyl rings. And they're structurally different. This is much bulkier, but electronically similar because this is a metacoupled system. So it's not really contributing electronically to the system. And so our parents would be the 2,6 M and P, phenyl and M-terphenyl, and the 4,8 P and M, and then these would be the proposed children. And so in the essence of time, I won't show you the synthesis, and I won't even go into too much detail about about this slide for the electronic properties, but we overlaid all of the family sets. And we looked at the absorption and the emission spectrum, and we looked at it and we were like, it didn't seem to have rhyme or reason in terms of the absorption spectrum. Actually, we were a little bit disappointed. This is one example here. And so we can see the teal is actually the child. And here is one parent, it was broadly absorbing. The other parent was narrow and redshifted. The child looks like this, but then it's kind of shifted more like the other one. So we thought, and most of them went this way. Some of them were even weirder. We could see this child looked more like one of its parents and completely ignored the absorption property, at least in terms of the characteristics of the other parent. And so it kind of went that way. And we were a little bit disappointed, like, it's not predictive. It's not really predictive at all. And then it varied which one would dominate. We saw that if, like in this case, both parents are M and the other parents are P. So we were disappointed. And this is actually my favorite one. You can see it's completely crazy. Here is the child, it's purple. The child is one is here is purple. It's bimodal absorption. The one parent has a very broad absorption, and then the other parent has a singular strong absorption. And in that region, the child actually has a node. It's almost like the child chose exactly to go opposite the parent in this region. Here is like total missing. So he's like, okay, not predictive in the emission, completely disappointing. But then we start to look at the HOMO and the LUMO. And this is where we got excited because it turns out that what was completely predictive was the HOMO and the LUMO. In every instance, here we plot and we gas phase measurements, and these are theoretical values versus the measured values. These are the calculated values versus the measured values. They're a little bit cleaner, but the trends hold on the experimental too. Here we can group these things together by family. So here's a family set. This is the child that comes from the 2,6M and the 4,8P. And what we can see here, here's the LUMO for the 2,6 parent. Here's the LUMO for the child. And this is the LUMO for the 4,8 parent. And so we can see that this child got its LUMO from this parent. And then if we go down here, here's the HOMO for the child in orange. Here's the HOMO level for the parent. And this child got its HOMO from the 4,8 parent. And it's consistent all the way throughout, with little exception. This one's a little bit weird. We don't know why these two got crossed over. We checked and double checked. It's real. That's real life for you. But without fail, even if the numbers aren't exact, the trend holds. We can almost say without fail that based on the linear parent, the 4-8 parent is going to determine the HOMO, and the 2-6 parent is going to determine the LUMO. And that was the exciting outcome, because that's the predictive property that we were looking for. So now that tells us, not only do we look at what the energetics are of the heterocycles that we choose, but now it tells us what is the relationship between their position and ultimately the properties of the systems that will come from it. So future considerations, I point you to William and Kate, the ultimate royal family. In many ways, we're guilty of kind of having a William and Kate situation. And for those of you who follow the royals, when they do the bloodlines for the royals, you can almost inevitably find out that they all have like a common ancestor. They're all were royal way back when, and they kind of married within the family. And I bring them up just to say that when we go back to our systems, they were all benzols, so they weren't that different. And so we said, okay, it held good. It held up in a really safe system with a lot of similarities. So we're going to go to the other extreme next. We're going to mix together two systems that are very different and see what happens. And so now we have the other royals. We have Meghan and Harry. And in fact, look at little baby Archie, right? I can't wait to see how he looks when he gets older, but he's already going to be interesting. He's got some interesting genetics coming between his dad's red hair and his mom's dark hair and mixed race and everything. So we're going to more go to the other extreme. So we're going to pick two systems that are very different and see if our predictive properties hold. And we're optimistic that it will. Why are we excited about this? Because if we can figure out, I mentioned in the beginning about white light comes from orthogonally paired systems, something that's orange and something that's blue. If we can make both parents that are orthogonally paired and combine them in a single molecule, then we can start to push toward a single molecule that emits white light. And these are some of the images of some of our solids under a UV lamp, and we can see bluish white, yellowish white, orangish white. So there's potential for white there. So if we can actually refine the substituents, we can really get down to the white light emitting material from a single species. So with that, I'm gonna close out. This is a little summary. I kind of said what I was going to do. I wanted to show you how our platform worked. It worked, and we've got the results. This is our really swanky device fabrication lab where we make our OLEDs. I'm super proud of that. We spent a lot of money and a lot of time building it, and we're excited to have it. And I thank you all for your time. I'll just pop up the lovely people who did the work and thank them. But I'd like to open up the floor, the remaining time for questions. I just welcome all your questions. Yeah, these are, even now I got to update. We haven't been in person since last year, so we haven't taken a new group photo. But even since then, I mentioned that they all run off and leave me. Carmen and Evan and Jess, they've bailed. They got jobs. They've all even got great jobs. Yeah, actually in this picture, only people who are left in this picture, me, David, and Amy. I'm buried behind my picture, at least. And Ramiro, I mentioned he's already gone. And Alfred, these guys are gone. They finished at the beginning of the year. So all these guys are gone. But me, David, and Amy, and these two are looking at the front door. But I got new ones coming in. Tatiana here was she was a summer student, so I knew I wouldn't keep her very long. But I inspired her to go on to college, and so that's great. Anyway, questions.
You guys could put questions in the chat, or you can unmute yourself and ask a question. Either one will work with me. While people are thinking about questions, I have a question. It's kind of, at least to me, strikes me a little curious. You were trained organic chemistry. When I was trained in organic chemistry, I didn't have any clue about material science and some of the stuff that you talked about here today. So was there some sort of transition that you made from being a synthetic chemist? You're still a synthetic chemist at heart, right?
Mm-hmm.
I mean,
yes.
You said that up front, but the application, many times organic chemists may do applications in the biological side,
mm-hmm.
but you chose like the material side. Could I get a little bit more insight there?
Definitely. I definitely say that, first of all, the material side is it is interesting how there's like everyone accepts the fact that people from organic can become bioorganic or become more biological, but by the same stretch of the imagination, there's plenty of opportunities for organic chemists in the material side and physical chemists too. In my experience, and me and my chemistry colleagues, we make fun of some people do go to school and get degrees in material science. We kind of like, well, what is that? Because it's so because it's so applied, and we actually feel like, being grounded in something fundamental, is a strength. And we see this sometimes we deal with true material scientists. We start talking about like, homos and lumos. Like, oh, okay, well, what's going on? And they're like, wait, what's the homo? And you have to like, okay, the valence band. Like, oh, okay, because they're used to the application. And so the tools that you have as a classically trained chemist will serve you well if you decide to go into the material science space, and you can learn the applied. If you understand the fundamental, you will be able to quickly learn the applied. I find that the reverse is not true. If you start off, which is what engineering is, it's more the applied chemistry. Often people, they're great at the application of it, but when something fails and they have to really troubleshoot and they don't understand the fundamentals behind it, that's where those students struggle. So I tell students like, yeah, if you want to do material science, major in chemistry, major in physics. Don't feel like you have to major in materials engineering or something. You can switch and at the doctoral level quite easily. For me, the switch just came from being in, it was when I was getting my degree, the field was just getting started of this organic electronics, and it just seemed so crazy. But I like synthesis and I like putting things together. And I said, well, let me get it straight. This field is predicated on the ability to put together large amounts of heterocycles. Like, oh, sign me up. Because I just like making things. And I remember when I did a brief rotation in a Medichem lab, and I remember just watching them get milligrams of materials after doing like 18 step, multi-step synthesis, right? 18 steps. And then, and then you do it and you have the wrong stereoisomer, right? Oh man, you're like, dang it, it's S. It's always supposed to be R. And so, I saw that and I thought that can't be my life. And so I like and the students who work for me, they love it because you do the synthesis and, we're always getting our solutions. And my students always send me pictures like, actually we even have a group, we have a group Instagram where I put in pictures and like all of our stuff is like fluorescent, it's cool colors, it's interesting, and it's interesting every step of the way. And that just lured me right in. But yeah, I just was sitting there looking at them, looking at that multi-step synthesis, like, wait, you mean to tell me you got like 7 steps in and realized it was the wrong stereoisomer? Like, oh my God. And so I just got drawn in, and a lot of it I've had to evolve as a scientist. You learn along the way. I mean, my PhD was in just straight polymer synthesis. It wasn't applied, and then it was in my postdoc that I picked all. I did a postdoc, and that's true of any postdoc. A lot of people who are regular chem who become more bio might do a biology postdoc, and and so on and so forth. And so that's where you really can start to pivot is later on.
Okay, so anybody has questions? Okay, you could do in the chat or you can unmute. So I have another question. So it sounds like you have 2 holy grails. One is getting really blue, and the other is this thing you were talking about with the white. Is that correct?
Yeah, and they're actually interrelated, because I mentioned to get white, you need basically colors from opposite sides of the color wheel. So orange and blue is the typical combination to get white from 2 components. Some people do like a tri-component system, but orange, which also involve yellow, but a nice orange emitter, and there are a lot of known orange emitters paired with a nice blue is what can get you white. Or as we hope to actually have the single emission coming from 2 unique chromophores in the same system. And so if we can solve the blue problem, then that can be an active component for regular displays, but also for lighting. And so that's why we felt like there was tremendous opportunity in the blue.
Okay. I have a question from Nicholas. It's kind of in the same vein, I guess. What caused you to go down this path in your life? What inspired you specifically? I guess maybe it's a broader question of maybe chemistry.
No, yeah, like specific. Well, I can tell you 2 things, Nicholas. In the beginning, in terms of what inspired me to be a chemist at all, I was always wired. I mean, if you ask me, I was born to be a chemist, even before I knew what being a chemist was. I was always that kid who was like, well, why does that happen? I remember I get into conversation, and my poor mother, your kid is like asking, this is like something your mother would dread unless I don't have children. If my children hit me with that, I'm ready. But my mother did not have a PhD in chemistry. And I remember asking my mother, like, why does water boil and why does wax melt? How come wax melts instead of just, burning away like paper does? And, I'm hitting her with all these questions, and she's looking at me like, I'm and my mother's old school. She went to school, and they still majored in home ec and things like that, right? Home economics and stuff. And my mother's like, I'm a seamstress who majored in home economics. Like, why are you asking me this? And so that was kind of my life growing up. I was always inquisitive, but my mother did, and you younger people are like, wait, what? I'm older, so we didn't have the internet, and we certainly didn't have it at home. And so my mother would like drop me off at the library, like I don't, Malika, I don't know. I bet it's in a book. And we would just like go to the library. Like she had me reading Encyclopedia Britannica and like reading like, advanced text, like looking for answers. And she would, pack me a snack and just let me loose in the library. Like, I don't know, but I bet the answers are in here. Like, go figure it out. And that was kind of my childhood. And then I was fortunate enough to do a summer camp for girls. It was summer science camp for girls. My mother found, and she sent me there, and I came home and I was like, I'm gonna be a chemist. She says, okay, why are you gonna be a chemist? I said, that's a chemist's job. A chemist's mom is supposed to heat, mix, stir, and find out what would happen. And I had my very 12-year-old knowledge of they had given us a periodic table and told us that you can combine different atoms and make the elements can make the molecules, and the molecules can do things. And I'm 12 years old, like, yeah, I want to make molecules. Like that's what, and there's so many molecules you can make, and we don't even know what happened could do, mom. And she said, somebody, my mom was very practical. Somebody gonna pay you to do this? I said, yeah, there are plenty of jobs in chemistry. She's okay, then do it, go for it. And and that's kind of how it began. And so, I went through the paces, and and how I found my identity with this particular field. I sat in somebody else's talk. This gentleman came to my school, much like I'm here giving a talk, and he was one of the forefront leaders in the field at the time, a pioneer, a guy named Richard McCullough. And I remember hearing him talk, and I was like, both excited about what he had accomplished and just hearing how open-ended the questions were. Like there was so much work left to do. And then I thought, well, this is okay. They need people to make molecules and these type of molecules and then figure out what happens. Sign me up. And so it was fun. And then I worked with him and I learned a lot from him. But then what was fun was seeing my own evolution, whereas I started in the same vein as him in terms of the questions and the inquiry. Along the way, and you'll do this too, I read a lot, and you read, and then I learned that I was still interested in things that I was doing with him, but he wasn't doing OLEDs, that I was really fascinated with this OLED question, and that my skill set was translatable. So when I started my own research program, I also started to look into the OLEDs.
So I'm just wondering about using other atoms like selenium instead of sulfur, or phosphorus instead of nitrogen. Are people doing that sort of thing? Are you interested in doing that sort of thing? Do you have opinions?
We do.
Okay.
Yeah, and adding larger atoms. There's a phenomenon that we call like the heavy atom effect, because you have that extra level of valence electrons, and it does change things. Sometimes in a good way and sometimes in a bad way. And so there are people who that's their niche. Like I said, my niche is to chase after blue. Some people say, oh, well, everybody's just using carbon, oxygen, and sulfur. I'm going to use selenium, tellurium, and phosphorus. I actually know a guy at Case Western who he actually makes phosphoxazoles. So he makes the bisoxazoles, but he has the phosphorus there instead of the nitrogen. And so that's his deal. And I know a guy in Canada, and he's doing a lot of things, and he's looking at selenium and tellurium based heterocycles instead of sulfur and oxygen ones. So absolutely. I remember I saw talk once, a guy in Japan actually made lead heterocycles.
Oh, lead.
It was crazy.
Yeah, I haven't seen that one.
No, I was like, wow, it's crazy. Yeah, that's like my crew. We get together every other year to have a meeting for people like me who just want to make things, and what people report out on, you're just like, brilliant and good for you. Oh, I have a question. Let's see. Jacob says.
Jacob, yes. Once you reach
the level of blue. Yeah. Right, Jacob? Because this is, it's almost like a good movie, right? You have to figure out how to get your, you want to get your trilogy out of it, how to keep it going. I don't ever think we'll get to the point like, okay, we got blue, mic drop, walk off the stage. But I do think that there's always opportunities for refinement. So step one is like, how do we get the best blue possible? That's option number one. And then option number two is sometimes once you get there, when you reflect on what you did to get there, it's not necessarily the most efficient or reasonable synthesis. So then the second step might be like, now that we learn what are the key criteria or the molecular attributes that contribute to blue light? How can we make systems that have less synthetic steps? Because I mentioned, like, I like my little two-step synthesis, although that was a little bit of a simplification because we had to do a couple of steps to get those units together to ready to combine them. But yeah, once we really understand what the key attributes are molecularly that lead to blue, then thinking about what the most efficient synthetic pathways are to achieve that would be the next step.
Mhm. Yeah, I think I just recently saw a research report, actually late last year, early this year, of someone who discovered perovskite, I'm pronouncing it,
Oh, perovskite.
perovskite, that
Perovskite.
is both conductive and transparent.
Mhm.
And it sounded like it was a big deal. I
Yeah,
can't
so
remember.
perovskite is the next technology that's kind of challenging silicon for solar energy conversion.
Okay.
Um, And so the two extremes I mentioned, silicon is kind of king. It's the old established existing heterocycle, and people use it a lot for different things. And then we're doing the organic side. One of the things that people like about organics is we can make transparent devices. I mentioned the flexible, and you saw some of the pictures in my examples. You could see that there was a level of transparency. And if you think about the solar cells you see along like the highways and stuff, they're kind of gray, flat, right? They're just big things.
Mhm.
The nice thing about transparent, and we're seeing some of this technology actually coming out of Europe, you could potentially, if you have a transparent solar cell, you could actually put it on make it part of your window. And so
Hmm.
you can actually catch the solar light that's entering a room and
Hmm.
use it, capture it, a percentage of it as energy and use it to heat or cool that space. And
Ah,
so if
okay.
your material has to have a level of transparency because you don't want to black out the room. Nobody wants blackout windows. And
Right.
it doesn't have to be completely transparent. In fact, most of these things tend to be kind of bluish, greenish, or brownish, which
Oh,
if you look at like skyscrapers, they like having tinted windows anyway. So if you can actually have something that has a cool, like, slightly tinted window effect, and it's actually a passive solar device, that's a huge boon. And so people see that these transparent perovskites as being an opportunity. One of my students actually gave a talk earlier today, and I think she nailed it. She said, in the beginning, people used to judge us for not being as good as silicon, but we don't have to be as good as silicon. We're different from silicon. And I think like trying to plug in this technology where existing technology is working is the mistake. We need to plug in this technology where existing technology can't go.
right, right. Yeah. Be
And so
more.
yeah, like you're not going to be able to coat a building with silicon panels and make electricity out of it. They always end up on your roof.
Yeah. 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 All right. Anybody else has questions? Anaya, you have a long question. Do you want to unmute and ask a question? Anaya is in Trinidad. Yeah.
Hi, good evening. I know you said that to make the white light you would need a blue and another color from the other side of the color wheel, like orange. And I was wondering if you guys tried placing two parent molecules together to make the one child molecule. What was the white like? Like, was it an orangish white or bluish white? And if so, what would be the necessary steps to make the light more white so wouldn't need.
Excellent. Thank you for your question. And are you really in Trinidad?
Yes, she is.
Yes, I
That
am.
is that is awesome. I need to. That is awesome. I want to visit there. I want to get out of here. I want
We-
I want to go somewhere with a beach
Between Anaya and I, we'll hook you
We
up.
would love to have you.
oh my goodness. Actually, it's funny. One of my friends is actually, she's at a small college in St. Lucia. She's, oh, Malika, would you ever come down? Would you ever be willing to come to St. Lucia and meet my students? And I was like, you had me at St. Lucia. Like, are you kidding me? Anyway, thank you for your question. Yeah, so that is our goal. And so now that we really kind of are honing into this parent-children thing, at least we know a lot about the energetics. That's step one. But like I mentioned, unfortunately, the absorption properties weren't particularly predictive from the experimental side. So we're doing a lot more, what my students say, in silo with the computers, especially with our lab having shut down last year with COVID and everything, to do some computations to try to figure out. But I do think that we can get there. Some of the systems we have made are yellow, and so then you have to ask the question like, okay, which one and we're digging into the literature. I mentioned, if you know the fundamentals, you can figure out the applied. So then we said, okay, we're actually overhued. So which one is over? Is it not blue enough, or is the orange too red, or is it too yellow? Like, which one is it? And so this is the space we're kind of circling around now, trying to understand more. But I think we're going to be able to get there. I think we're going to be able to get there. The other caveat is, although we'd like to say that they behave as like two completely different systems, and that seems to be true for the HOMO level and the LUMO level, the emission does seem to be a little bit of a hybrid, more one part parent than the other, but it's not completely that. And that's the variable we're having a hard time predicting. So we may say, oh, okay, but the emission seems to be like 75%, mom and 25% dad. So how do we now modify that to compensate for the fact that we're not getting a full contribution from one side? So these are the things we're still figuring out. So it's going to take some time, but the good news is, it's good when you have time. You can make a plea to the funding agency to give you a renewal and keep the project going. So we're glad we haven't solved it yet.
All right. Anybody else has questions? I think we'll go ahead and wrap up if nobody else has questions. I have more, but we'll see. Anyway.
Maybe I have a question.
Okay.
I do have a question, not me.
Okay.
So basically you're describing computational chemistry to predict or whatnot the different trends that you might see in the colors. How did the computational chemistry do a good job of predicting just the trends, or was it kind of numerically accurate in terms of the band gaps or absorption features or whatever?
The computational chemistry is very accurate in predicting the HOMO. Okay. And it's good at giving us the trends. But the LUMO, the error lies in obviously, and for, what we're predicting, if you think about what a LUMO is, it's the lowest unoccupied molecular orbital. So we're predicting where the electron is not. And so the error in the LUMO is the highest. And so sometimes that obviously, when the band gap is higher or lower than we anticipate, it's usually due to error in the LUMO measurement. But the trends, what we can definitely say is maybe our number is not going to be exact, but if the theory tells us this system has a smaller band gap than that other system, that always holds true. But the delta, the how much smaller, is the variable that the accuracy fails us.
Do you know if the collaborators just did calculations where they were calculating the energy of the bottom one? This is HOMO, and then the LUMO, or did they actually do like the TD-DFT where you can like calculate the actual absorption energies? Because
no, she actually calculates the absorption energies. Yeah.
Okay. Yeah.
And things get better. I mean, we've done once we got real data, and we're actually starting to evolve, because when she predicted things, and then once we make things, and once we can actually see how the real numbers are stacking up against the calculated numbers, then she went in and tried different correlations and different basis sets. Whatever, yeah, different models. Yeah. So then she tried to look, because actually the original model we did the work at, we don't even use anymore, because we went through tested 15 different combinations of basis sets and correlation factors and stuff. And said, this one is more accurate. And we have another collaborator, which is great, a guy I crossed paths with, and he was into machine learning. And so now we're giving them our numbers, and now the computer calculated some stuff, we made it, and now we're telling them what we got. So they're telling the computer, well, this is actually what it is, and it's hopeful that the computer can then come up with its own type of correction once it knows how much the fashion, which is, if it can actually start to predict how it's overshooting using technique A, TD-DFT, if it's overshooting, then if they actually could say, okay, but it usually overshoots in this fashion, so here's a correction factor, here's your actual number. That's what we're hoping will come from that.
Yeah, very good.
Yeah,
those things, it's always kind of very black boxy, and there's always one more level of theory you can do, right? So
yes.
AI,
I mean, we dabbled a little. Yeah, the AI part is really, I find it fascinating to even be a part of it. To be like, I'm contributing to AI.
Super. And the screens to program it on too. Yeah, with
Yes.
the OLED research.
Yes,
yeah.
absolutely. It's actually funny. My theory person, when we had to start to go to work from home, she was like, I don't care if they reopen my campus. I took all my monitors home. I'm not going back.
All right, sounds good. Sounds good. So again, we want to thank you very much for a very great lecture and enthusiasm. Like you got a lot of it. Do you bottle up enthusiasm?
Oh man, I just I love what I do. I love what I don't get me started. When you get me talking about science, I love what I do. So I'm like, oh, you want to talk about my science? Like, yay! I'll tell you why we do the crazy things we do. So thank you. Thank you for your patience. I'm so glad I was finally able to do this. We'll do it again in a few years, and it won't be 15. We'll do it again in less than 15. We'll do it again in less than 15 years when I have my white light. I hope that y'all come back in again in a few years, and I'll have my white situation all figured out, and I'll be happy to tell you about it.
That's a promise.
You got it. You got it.
Okay, thank you very much.
Thank you everybody for coming.
Thank you.
Bye-bye.
Bye-bye.